The Reynolds average Navier-Stokes then comes from this Reynolds splitting in a mean part and a fluctuating part. Velocity, pressure, density, whatever, and you can then write the Raun's equations on this form. Total derivative of the mean velocity field, mean pressure gradient, gravity or whatever. Then you have the viscous stresses here, and then you see we have thrown these Reynolds stresses on the other side, so they become negative. So you can ask why. Why have we written it in a form like this? Well, if we write it a little bit differently, it might be easier to see. So the final term there was the dxj of a sigma ij, and then minus rho ui uj time averaged. We had it on this form. What will this guy look like? Well, if you have the density with you, yes, you can write him on the form the viscosity, and now the dynamic viscosity, multiplied with du I dxj plus duj dxi. There you will have the viscous stresses. And now this one, of course, density multiplied with the kinematic viscosity. And this one then being constant for a Newtonian fluid, that's okay. Still we keep him inside this derivative, and the reason is going to be quite apparent. We are going to model this guy in sort of exactly the same way. We are using the mean field gradients, and then we multiply not with the real viscosity, but with a invented turbulent viscosity. Then you have them on the same form. Very easy to handle in a program. So sort of a pragmatic solution, but simple. So I mean, the pioneers here, they had to do something when they came up with this equation, how to handle this term. So the reason for throwing it on the other side is sort of physically to say that this turbulent motion here acts as a viscous term. You sort of have a turbulent viscosity damping out the motion or any gradients. So we say the Reynolds stresses, then we just define it as the negative of these time average fluctuating velocities. And how to describe it, as I said, that's the job for a turbulence model. And for the easy part in this family of turbulence models, the Raun's family, they will be based on this eddy viscosity hypothesis. And there you see it. You say the correct Reynolds stresses, impossible to find accurately or hard to find accurately, we model them. And as a model, yes, we use this eddy viscosity concept. And then we use the same mean flow stresses, which you have already. So what you actually then have to do in your equation, very simple, you simply do the following. we say this one will now be included here. That's it. So all you need now is finding an eddy viscosity. Then you have it. That's all. Very easy. So this eddy viscosity hypothesis, sort of the birthplace for the zero equation models, 1, 2 equation models. For the more advanced, a full Reynolds stress, then you don't do this trick. Then we are going to find all of these guys directly. That's something else. But for now, we do this nasty little trick. Very simple. Finding now the eddy viscosity is our job. Okay? We have an additional strange thing here. You have a Kronecker delta, then equals 1 when I equals j, 0 else. Why do we have him? Well, he has to be there for the expression here to be correct. This one normally doesn't introduce any problems. Well, first of all, this little k here, we haven't defined him yet. He should pop up down here somewhere. Yes, this is actually wrong. It should be ui. Remember the tensor notation? When the indexes are the same, that means automatically sum up over all indexes. So this being the turbulent kinetic energy should read 1/2 of u flux square plus v flux square plus w flux square. So that is sort of the trace of this diagonal when you sum it up. So here you have the turbulent kinetic energy, and normally what you do, you take this term out of the viscous term and you join it with the pressure. So you just adjust the pressure a little bit with this term. Normally not a problem at all. Okay, now we are a little bit better off. We had here 6 unknown functions, all 6. It's a full Reynolds stress model. It's actually a matrix consisting of 9 functions, but it's symmetric. So uv equals vu. Hence, you have 6 different functions in the 3x3 matrix. We have reduced these 6 unknowns to one function that has to be found. Well, actually 2. If you look at the turbulent kinetic energy as well, we're going to need him also. So here, in this text, then I jump directly for the 2 equation models. That's fair enough. Now, set up a transport equation, a full differential transport equation. You can do this without any calculation. You can just throw it up directly. The change of any quantity equals, then you have several terms. You have something that produces this quantity. You have something that diffuses it, sort of move it around within a volume. And then you have something that destroys it, some dissipation. So for any transport property, of course, these 3 terms has to be present. Something that creates it, something that destroys it, something that's moving it around. So, of course, instead of going this way, you can find the real equation for K by this Reynolds average Navier-Stokes and doing some manipulation there, as I told you. So yes, you can find exactly what these terms look like analytically. But that really doesn't help you because you can't solve it anyway. They are way too complex in general. So you can just as well start here by just saying that, okay, I want a production term, I want a diffusion term, and a dissipation term. And then model them, because you have to model them anyway. So as it says, the exact transport equation for K, that's not something that's practically useful. You can't really do anything with it. So the exception, you might say, is the production term. This is what it looks like, correct, just precise. So here you might say, whoa, we now have included these unknowns, the Reynolds stresses, for the production term. Okay, but now we are going to use the eddy viscosity hypothesis anyway, so we can replace him with this guy. So there we have then a decent model for the production term. The other terms, the diffusion and also the dissipation, that's a different story. Diffusion is very complex indeed, has to be modeled. And the dissipation, I'll show you later how actually he looks. And well, I think I have it here. Let's just have a check. It's not that one, this one. View. There you have the correct transport equation for an epsilon, for the dissipation. So here on the right hand side you will now have something which will be a production term, something that's a diffusion term, and something that is a dissipation term. So here actually you have a complete analytically correct transport equation for this unknown epsilon. And if you start looking at the different terms here, you are in very deep trouble, of course. Very complex terms. Here in this text, the small velocities, they don't have this apostrophe, so the small letters, they are the fluctuating velocities, not the real ones. And the large one, that is the mean velocity field. So here you have one term with the gradient of the mean field in front of it. So that then should be something like a production term. When you have a gradient in front, derivative in front, that should be a diffusion term. And down here, whatever is left should then be the dissipation term. Here is a little strange. Remember, we are talking about the dissipation. That means the destruction of turbulent kinetic energy. And how does this quantity behave? How does it change? Well, you have something that produces this quantity. So that's production of destruction. And then here you'll have destruction of destruction. So it's not easy to understand this one physically. But in the end, you see, we have no way of calculating all these complex terms correctly. So the quick and dirty version, forget it. You can't do this. So it's impossible. They're way too complex. You can't even go to the lab and measure all these quantities and see how they actually, what they should look like. Here you have, for instance, pressure and velocity gradients in the same point. How can you measure pressure and velocity in the same point in the lab? Nobody has done it yet. It can't really be done, because if you want to measure a pressure, you have to go in with a probe or something, and then you destroy the velocity field. So forget it. We have no idea how these terms look like. So no, it can't be done. So same goes with the full Reynolds stress. Here you have a transport equation, the analytical transport equation for the Reynolds stresses. And if you here say J equals I, you will actually have a transport equation for K, for the turbulent kinetic energy. But again, on the other side here, terrible. The production term, that's the only one that sort of makes a little bit sense that we can handle. Here you'll have the function multiplied with the gradient of the mean field. So that's something that we actually can get something sense of. But all the rest, you can just forget it. You have no chance to calculate these quantities correctly. They are way too complex. So it has to be modeled anyway. So yes, you could start here, but you won't really get anywhere in. So for instance here, this one we then call an epsilon. And we now say, okay, this is something that destroys the Reynolds stresses. Then, okay, then we have to model this part. Here, diffusion terms. No way we can handle this one, so we just create a diffusion term as a model. Come back to this later. So, production, diffusion, dissipation. That's what we need. Production term, okay, but the other two has to be modeled, and for a two-equation model, the K epsilon model, which is the focus here, of course, this guy is described, is modeled with its own transport equation. This term, well, there we need a modeled term. So, I'm not sure if he wrote it out here. No, he didn't. Well, never mind. So with the K epsilon model, you'll have two transport equations, one for K and one for epsilon. But what we needed was the eddy viscosity. So then we can close the equation system by help of the Prandtl-Kolmogorov. They did some dimensional analysis and then find a connection here between the eddy viscosity, the unknown function, and K and epsilon. And the connection is written here. So you find K, you find epsilon, and then you can calculate the eddy viscosity, which is the quantity that enters into the Navier-Stokes. So that's the final equation needed. Two transport equations, one for K, one for epsilon, and this algebraic equation. That's all you need. This two-equation model is widely popular, the most popular in CFD, and fairly straightforward to use. You don't have that many coefficients, constants, into the model. For the classical one, I think only you have two. So that means for a given problem, you sort of have a standard set of these constants. They have to be, of course, found by numbers. So a little bit depending on your problem, then you have to find a proper value of these coefficients. But I think it's only two in the standard K epsilon model. For a full Reynolds stress model, you'll have about 20 to 25 constants. So then you have to tune the model against your problem. So that's a different story. Here, fairly simple. Only a couple of constants. A full Reynolds stress model, then we don't cheat, you might say. Then we don't use the eddy viscosity hypothesis. We are solving these transport equations directly. So then we are talking full transport equation of each of the different Reynolds stresses. And we had 6 of them. And here again, you set up a transport equation. The change of a Reynolds stress equals something that produces it, something that diffuses it, and something that destroys it. And then we have one additional term that we haven't seen before, something that was not present in the transport equation for either K or epsilon. This one, it's a redistribution term. He can take energy from one of these components and give it to some of the others. So I think they call it also a pressure strain term. And going back to the analytical expression here, here you have the correct analytical expression for the Reynolds stress. And here, this term we define as this phi ij, the redistribution term, or as you see, pressure and strain, pressure strain term. But think of it as a redistribution term. So he will be, say, positive for one of these components and then negative for some of the others. So he takes energy from one and give it to some of the others. It's a complex term though. You have pressure fluctuations multiplied with the gradients of these velocity fluctuations and then time averaged. So not easy to see how that one behaves. So yes, of course, it has to be modeled somehow. For a full Reynolds stress model, then you see also here, now the production term is exact, is correct. You don't have to model this one. These are unknown already, and these are the gradients for the mean velocity field, which we have. But the rest has to be modeled. One model that is quite standard is the last one here, the dissipation of Reynolds stress. Here you will actually have 6 different dissipation functions. So for each of the Reynolds stress, you should have their own private dissipation. But sort of everybody has agreed this is not worth the effort. We are going to do a lot of wrong here anyway. So we just create one single epsilon to cover for all 6 functions. I mean, this is complex enough. People have tried with modeling, well, actually not modeling, but taking the different terms here and then try to find now, for instance, here a transport equation for this quantity, a triple correlation, and see how he looks. I've seen it once, the transport equation for this quantity, and it went over several pages. It was extremely complex. But the philosophy were something like this. The higher order of these different terms that you now try to construct a model for, the more error you are going to do, but the error is going to be less and less important. So they hoped that they could gain or create crude transport models for each of the different terms, and then finally obtaining a more correct model. They were wrong. It didn't work. So no, we are still left with just forget the analytical expression, model them. Except this one. This one is correct. Yeah. So here, production term, as it says, no need to model this one. So there we have control. And also now we have this one covered. It's the same transport equation for the epsilon as we use in the standard K epsilon model. So we are left with these 2 terms. They have to be modeled. Now for the ASM. If you can recall, You had, in the Rans family, you had 0 equation, you had 1 equation model, you had 2 equation model where you find k epsilon, and then you had ASM, and then you had a full Reynolds stress model. The full Reynolds stress model, that was 1 transport equation for each of the 6 Reynolds stresses, plus a transport equation for epsilon. The ASM is now a very cheap way of obtaining the different Reynolds stresses based on a solution from a 2 equation model. So you start here by using k epsilon and simulate and get a solution. Then you switch on the ASM model. That's just a set of algebraic equations. You can see here. No differential equation, no transport equation. So when you have k and epsilon, then you can calculate these 6 Reynolds stresses fairly easy, very cheap. So that's actually a very, very good idea if you do a simulation and you're using k epsilon or k omega, whatever, and you have an answer and you are a little skeptical to the answer. You're not sure that this one is correct. Then you can switch on the ASM model. It's very cheap. It doesn't cost much to sort of update your solution and see if something changes. Because this one, he covers much more physics than a 2 equation model. Much more. So there you can sort of arrest your simulation. If you have a lot of changes, then you know a 2 equation model is not good enough. And the short version why the 2 equation model will fail is that he is blind for directions. Typically you will have a transport equation for k and the transport equation of another quantity, epsilon, omega, whatever. But remember, k being turbulent kinetic energy, that's the velocity squared. So he doesn't have any sense of direction at all. So he is sort of dependent on the philosophy that the turbulence is isotropic. And for many, many problems, that's a big lie. You will have directions where the turbulent will behave quite differently than looking in another direction. So there it could be a very good idea to switch on an ASM to try to detect the different Reynolds stresses. So an ASM, that's definitely something that's worth remembering. Very good one. And very cheap. Doesn't cost much. In this text, they then now focusing on turbines, pumps, rotational machinery, and we have a couple of examples that we are going to have a look into why then these classical methods fail, the 2 equation models, why they fail. So of course we have very complex geometry. You have moving parts inside pumps, turbines. Not easy to see what's going on here, and yes, you may have both secondary structures. The flow may separate. You can even have cavitation. You can have a lot of problems inside these machineries, but we are here focusing on the turbulence modeling part, you might say. I won't go through all this. So we are talking 2 different problems that we then are focusing on. You will have, when you have a flow following a curved wall, and actually the curvature doesn't have to be large. It can be quite weakly curved actually, when you have a channel like that, and when you have something that rotates, a rotating channel flow, then we are in trouble using the standard k epsilon models. So even here, a weakly curved surface, then the effect can be a little bit difficult. I won't go through the details in this argumentation they use here. I find it a little bit tricky. they are using the Reynolds stress model, coming up with some arguments which I find quite difficult to follow, actually, when you start looking at the different Reynolds stresses and which one is then generating the other, changing the production term for one creates more of the other, and so on. So the primary, secondary, it can be really complex to follow and not necessarily correct. So it doesn't cover the entire truth anyway. So, and I think it's hard to follow this line of argument. You can have a look if you're interested, but this is not something that I'm going to demand of you. So we instead are jumping into the two problems that we are going to focusing on: curved channels and rotating channels. And here, instead of using these arguments by looking into the different Reynolds stresses, see how the production of them changes, you just go to the physics directly. Easier. Yeah, I won't go through all this, but you have some figures here in the end that I want to have a look at. So a slightly curved channel, something that we are looking into, flow in a bend, and also a rotating flow. So we won't go through these, sort of boring. So this will now be the other example that we are going to look into, a rotating channel flow. So you have a pressure gradient pushing the flow through a pipe, and then you rotate the entire flow. I think this one is not correct, is it? No, it's not. It rotates the wrong way. If you have a positive rotation like this, then you will have the other way around, won't you? Suction side, low pressure, that's true. But then the velocity gradient won't look like this. It will be different. We will have a look at that. So you have a curved channel, and you have a rotating channel. And the curvature doesn't have to be strong. It can be quite weakly curved, actually. And then here we have a rotating channel. So let's say the point of rotation is here, and let's do it clockwise. So now what's going to happen? You have entering here a turbulent velocity profile looking something like this. And something like this. The higher Reynolds number, the sharper the shoulder will be, the smaller this boundary layer here will be. Well, actually, it's not a boundary layer. Say the near wall layer is going to be smaller and smaller for high Reynolds numbers. So for this flow, you'll have then some velocity in, say now here in this curved direction. What's going to happen? Well, if you are going to follow the geometry and make a turn, somebody has to push you in this direction. Clearly, when you have a velocity here, then yes, you need a force, or else you can't make the bend, which means you're going to have a pressure gradient here, and this pressure gradient then has to balance the centrifugal force. So you will have a pressure gradient in the radial direction, which then should balance the centrifugal force. So you will have high pressure up here and lower pressure in the radial direction, or else this will not actually work. And then you look at the velocity profile. I should have drawn it a little bit better. Let's see. Easier to see. Something like this. Say you are a little fluid particle entering somewhere up here. You have then an average velocity, which then provides you with a local pressure gradient so that you can make the turn. Now, this is a turbulent flow, so you'll have a lot of activity all over the place in all directions. So, say now somebody push you up. So, what's happening there? Okay, up there you will now have a bigger velocity than your surroundings. You will be faster than the other fluid elements up here. So you will be fast, meaning this term he will increase. He will be bigger than what this local pressure gradient requires. And what's then going to happen? Well, the centrifugal force is now bigger than the local pressure gradient. You will continue out. If you do the opposite, imagine that somebody kicks you a little bit down. Then what happens? Then you are going to be slow. You are slower than your surroundings, and your surroundings, they have sort of this balance okay. So the velocity squared balances this local pressure gradient. But what about you? Well, your velocity is now too small. This one is stronger than your centrifugal force. You will be pushed further in. So now we can conclude this part of the velocity profile is unstable. So the turbulence at this side is going to be increased. When you do some motion, you will actually enhance and stimulate this instability even further. So the turbulent activity should increase on the upper half. If you do the same downstairs, down here somewhere, and say somebody push you now a little bit up, what happens? Okay, you had this velocity, and up here you are now going to be slow. You are slow, your velocity here is smaller than what the local pressure gradient requires. He is then stronger, and then he will push you down again. And if somebody pushes you downstairs, you are fast, then your centrifugal force is stronger than the local pressure gradient, and you will be pushed back up again. Aha, stable. So the stable and unstable side, it's a sort of the same as they called here a pressure side and here a suction side. I mean, you have a high pressure here on top and then low pressure on the inside of the curve. And it's only a weak curvature that is needed, and then you will see quite strong effect on the turbulence due to this mechanism. And if you try to simulate this with an ordinary K epsilon or a K omega or whatever two-equation model, you will fail. He won't see the difference on these two sides. He will have the same turbulent activity, no matter what. So that is a classical trap for two-equation models. They will fail completely. That stable side, he can easily be so stable that your flow becomes laminar close to this suction side. That can happen. And I can promise you, if you use the standard K epsilon model or any of these standard two-equation models, one-equation models, he will explode. They really hate when your flow becomes laminar somewhere. If you look at the different models, you divide by K, you divide by epsilon. So if either of these two guys gets close to 0, everything will explode. Of course, the programmers, they cheat. So you have something here divided by K, you have something divided by epsilon. You have several of these terms in a standard K epsilon model. And of course, they don't program it like that. So they cheat. So here they have plus 10 to the minus 6 or something. So you'll find such programming cheats in all codes, yes, just to keep them stable. Doesn't necessarily have to be wrong that you cheat. You risk in a simulation that you're getting close to laminar flow, but not entirely laminar. And in a solution process, your algorithm may sort of try different solutions and then touch or getting close to a laminar solution during an iteration process, for instance. So you're going to need this way of cheating anyway. For a rotating channel, you will have the same effect. Again, let's draw this one a little bit more curved, easier to see. Something like this. What do we have here? When you have a velocity and you have rotation. Well, should that be a problem? Well, yes, you'll have some additional force called a Coriolis force in such a flow like this. And the Coriolis here will look something like this, minus 2 times the rotation vector cross with the relative velocity inside the channel. So typically what you do when you are simulating a rotating channel, you add a Coriolis force, sort of an external force, and then you follow the rotation. I mean, you discreticize this region and then say the rotation, that's sort of an external thing. Or else you had to use a moving mesh if you want to use an absolute coordinate system. That could be rather messy, actually. So what do we get here? You'll have the rotational vector will now go into the blackboard. So that's one vector cross with a relative velocity local to the channel will give you a force downwards. And here you will then have some sort of a pressure. When do we have it? Let's see if it's correct. Should balance now a pressure in the, say, y direction. I think. If you rotate it like this, the pressure should be actually negative. Shouldn't it? I think so. You have a high pressure up here, and on this side you will have a suction side when you do the rotation this way. So now let's see what happens. If you are here somewhere, you have sort of a balance between the local Coriolis force and the pressure gradient at this location. And now if somebody kicks you upstairs, then you will be slower than your surroundings. So your Coriolis force, he will be smaller, and then you should be, if he is smaller, then he should be, no, that's not correct. This one should continue in this direction, should be unstable on that side. I guess I need a sign here somewhere. Anyway, it should be possible to do the same logic with a rotational force. And down here you will then have the opposite effect, that any offset of a local force balance will then push you back again when you have an offset when you are slower or faster than your surroundings. I'm not sure about these signs. Anyway, the philosophy will be the same. The pressure side, again, will be an unstable side. The suction side will be damping down the turbulence, tending more and more towards a laminar flow. So what will the velocity profiles actually look like? Here or here? Well, on the stable side, it tends towards a laminar flow. And a laminar flow here is faster than a turbulent, so this velocity will now maybe look something like this. He's tending towards this laminar parabola with a much higher velocity. On the pressure side, this shoulder will be sharper and sharper, so he will be something like this and then flip, and then they will join. Same here, the pressure side will be more and more turbulent, but here more and more laminar-like. So you will have something like this. Which is why this figure is wrong. It should be flipped. So the pressure side, increasing the turbulence, should have a more and more turbulent-like profile. The suction side, tending towards a laminar flow, more and more like this parabola. And I think they have the same for the... No, they don't show it here. A little bit. Here, more and more laminar-like, more and more turbulent-like, sharper and sharper shoulder on the pressure side. Okay, any questions so far? Then we take a break.